We spend 90% of our lives inside rooms exactly like these: bedrooms, classrooms, offices, and cars. To our eyes, the air circulating inside these enclosed spaces looks perfectly clear. But with every breath we take, we are exhaling carbon dioxide. In a closed room, those invisible plumes of CO2 begin to pool and accumulate, steadily filling the space around us. If you step outside, the natural atmospheric background for carbon dioxide sits around 420 parts per million. That serves as our absolute baseline for fresh air. Bring a group of people inside, close the doors, and seal the windows. You now have a high density of occupants in a small volume of space, with restricted airflow. Under those conditions, that 420 parts per million baseline is quickly left behind. For decades, we have treated this rising CO2 level as a harmless indicator of stuffy air, or conversely, people panic, assuming a high reading means they are inhaling an immediate toxic poison. Neither interpretation is accurate. To actually understand what that CO2 number is telling us about our environment, we have to completely rebuild our mental model of the air we are breathing. Carbon dioxide is best understood as a proxy metric. It is a direct mathematical indicator of shared air, the fraction of the air in the room that has already been inside the lungs of someone else. This chart illustrates exactly how that proxy works. As the main CO2 trendline rises, it drags other unseen human emissions right up with it. We can clearly track the parallel accumulation of human bioeffluents, body odors, and the exhaled respiratory aerosols that often carry viruses. However, this proxy has severe blind spots. Notice these new data points appearing on the graph for radon and volatile organic compounds, chemicals off-gassing from furniture and paint. The rising CO2 trendline ignores them completely. A CO2 monitor is entirely blind to these pollutants, as well as outdoor traffic smog. This creates a specific paradox when you introduce an air purifier. If you turn on a HEPA filter, the aerosols and particulates trendline will plummet to zero. The viruses and dust are scrubbed from the air, but the CO2 molecules are gases. They pass right through the physical filter media, leaving the main CO2 line stubbornly high. A CO2 monitor will never be a comprehensive pollution detector, but it remains the absolute best tool we have to measure the exact rate at which human exhaust is replacing fresh outdoor air. When people buy these monitors, they often look for a single hard number, a sharp threshold where the air suddenly turns toxic. In everyday species, that cliff edge does not exist. The common belief is that 1,000 parts per million is an official health-based exposure limit set by engineering authorities. It is not. The 1,000 ppm benchmark actually originates from historical ventilation mathematics. It was calculated to ensure enough fresh air was moving through densely packed mid-century offices to dilute human body odor to an acceptable level. It was designed for olfactory comfort, not to prevent cognitive or physiological harm. At the other end of the spectrum is the assumption that any reading below 5,000 parts per million is perfectly fine for human comfort and learning. That 5,000 ppm ceiling belongs to organizations like OSHA and NIOSH. Those are occupational safety limits, engineered exclusively to protect industrial workers in factories and breweries from acute hazards and asphyxiation. They have nothing to do with optimizing a modern office or a third-grade classroom. If we rely on historical body odor standards or industrial survival limits to manage our homes and schools, we guarantee that we will mismanage the air we breathe. Instead of searching for binary safe versus toxic thresholds, we need to evaluate our indoor spaces using a risk gradient. This graphic maps the target carbon dioxide ranges we should actually aim for indoors. The optimal baseline for everyday occupied spaces is as close to the outdoor air as possible, which practically means maintaining a reading between 600 and 800 parts per million. As we move into the 800 to 1,000 ppm range, the air is generally acceptable for many spaces, but it indicates the ventilation is only moderate. It is a zone that requires watching, especially in settings that demand high cognitive focus or quality sleep. Sustained readings between 1,000 and 1,500 ppm mark a poor indoor environment. This level indicates a clear ventilation failure and signals the immediate need to open windows, turn on mechanical fans, or reduce the number of people in the room. Anything sustained between 1,500 and 2,500 ppm is very poor for standard occupancy, and breaching that 5,000 ppm industrial limit is a rapid safety escalation. At that point, you need to evacuate the space and investigate the source. The data on this latter is useful, but it ultimately serves to ground us back in the physical reality of our daily routines, sitting at our desks, sleeping in our bedrooms, and gathering in meeting rooms. A small carbon dioxide monitor sitting on your desk will not diagnose every pollutant, chemical, or virus hidden in the room, but it remains the single most precise, accessible instrument we have for revealing exactly when our shared air is accumulating faster than we can breathe. The scientific literature on indoor air quality contains a glaring contradiction. Rigorous, peer-reviewed studies disagree on whether 1,000 parts per million of carbon dioxide impairs the human brain, with some finding severe effects and others finding none at all. To resolve this, researchers use controlled human exposure and blinded crossover studies. They isolate subjects in chambers, holding variables like temperature and humidity constant, to ensure the gas itself is the only changing factor. This body of evidence suggests that transient cognitive effects occur at typical indoor levels, but the results remain highly heterogeneous across different study designs. Research follows 3 tracks. First, injecting pure carbon dioxide into a highly ventilated environment. Second, restricting fresh air, allowing carbon dioxide to rise alongside human bioeffluents, the metabolic waste we naturally exhale. Third, relying on real-world data gathered from actual offices and classrooms. Reconciling the data from these 3 tracks reveals the complete picture of indoor toxicology, providing a blueprint for modern architecture to protect human cognitive throughput. A landmark 2012 chamber study by researchers at the Lawrence Berkeley National Laboratory and SUNY provided the first major evidence of direct cognitive impairment. They used a highly ventilated space to prevent bioeffluents from building up, then injected ultra-pure CO2 to reach specific targets of 600, 1,000, and 2,500 parts per million. Researchers measured performance using the Strategic Management Simulation, which evaluates high-level executive function and crisis response across 9 cognitive domains. At 1,000 ppm, performance on 6 of those 9 domains declined by a statistically significant margin. When the room reached 2,500 ppm, scores on 7 of the 9 domains collapsed. Specifically, the participants' ability to handle basic strategy and utilize information dropped to a fraction of the baseline. In an attempt to replicate these findings in a more realistic setting, the Harvard T.H. Chan School of Public Health launched the CogFX studies. They tracked 24 knowledge workers over 6 days, manipulating the CO2 to 550, 945, and 1,400 parts per million while keeping ventilation high. Even at the moderate level of 945 ppm, average cognitive scores decreased by 15%. At 1,400 ppm, a level common in many offices, the scores plummeted by 50%. Mirroring the previous results, the participants remained capable of basic tasks, but their high-level strategy and crisis response capabilities were severely compromised. This data indicates that pure carbon dioxide directly targets executive brain networks. However, this is only one side of the research. Despite these clear signals, other research teams have struggled to replicate the cognitive crash at 1,000 ppm. A 2019 study by Scully and colleagues tested astronaut-like subjects in specialized chambers with concentrations reaching 5,000 ppm. Performance remained stable across the exposure range, with the data showing no consistent downward trend even at the highest levels. Similarly, a 2023 study by Chen and colleagues focused on short-term exposures in healthy adults. Their findings showing no link between CO2 and cognitive impairment for any concentration below 2,100 ppm. These conflicting studies often focused on different types of work, utilizing shorter durations and simpler algorithmic tasks rather than complex executive simulations. This suggests that human cognition does not uniformly fail at 1,000 ppm, pointing toward a hidden variable in the air. The central challenge for researchers was explaining why highly controlled chamber studies reached opposite conclusions. The missing factor is human bioeffluents, the metabolic volatile organic compounds and trace odors we emit with every breath. Researchers at the Technical University of Denmark designed an experiment to perfectly isolate these bioeffluents from the carbon dioxide itself. In one room, they maintained high airflow so bioeffluents were immediately flushed out, then injected pure CO2 until it hit 3,000 ppm. Under these conditions, basic task performance and typing speeds were completely unaffected, matching the results of the mill studies. In the second room, the airflow was restricted, allowing CO2 to rise to 3,000 ppm entirely through the subject's own exhalation. This allowed metabolic waste products like acetone and isoprene to accumulate alongside the gas. In this stuffy environment, subjects suffered from physiological stress, elevated heart rates, and headaches, which caused task performance to decline. These results align the previous research. Pure CO2 targets the prefrontal cortex during executive crisis management, the specific focus of the original Berkeley and Harvard tests. Conversely, the bioeffluents that build up when ventilation is low trigger generalized physical stress, which is what ruins basic algorithmic work speeds. The experimental contradiction disappears once we account for the fact that these studies measure two distinct biological failures based on how the gas was generated. While researchers can isolate these variables in a lab, the reality of building engineering is different. In offices and classrooms, carbon dioxide and bioeffluents rise in perfect tandem. When one increases, the other is always present. Industry experts have long debated whether CO2 is a direct neurotoxin or simply a tracer for underventilated air. For building operators and occupants, this distinction has no practical impact on how a space should be managed. A sustained CO2 reading above 1,000 ppm indicates a compromised environment, whether the damage comes from executive function loss, bioeffluent-induced stress, or both. To maintain peak performance, these spaces must be diluted with fresh air to keep concentrations in the 600 to 800 ppm range. Carbon dioxide stands as the definitive metric for human performance and physiological balance, demanding standards that look far beyond simple odor compliance. We tend to think of breathing as a mechanical purge, a forceful push of waste out of the body. But clearing carbon dioxide isn't a muscular exertion. It is a strictly passive process governed by the laws of thermodynamics. The entire mechanism relies on a partial pressure gradient, an invisible mathematical slope between the blood and the air resting inside your lungs. This alveolus model shows CO2 particles transferring seamlessly from blood into empty space, driven by higher natural pressure. In poorly ventilated rooms, inhaling elevated CO2 fills the alveolus, compressing the pressure gap and creating a thermodynamic bottleneck where off-gassing physically slows. This dynamic does not cause acute asphyxiation. Instead, it creates a subtle, chronic metabolic challenge. Because the gas cannot escape efficiently, the entire human biological system is forced into a state of constant compensation. When that exhalation gradient compresses, excess carbon dioxide has nowhere to go. It is forced to remain in the systemic venous circulation. Almost immediately, a chemical reaction occurs. Retained CO2 molecules hydrate in the blood to form carbonic acid, which instantly dissociates into bicarbonate and unbound hydrogen ions. These acidic ions cause a slight but critical drop in the blood's pH level. The brain has an internal chemical alarm system designed for exactly this moment, the central chemoreceptors located in the medulla oblongata. These receptors constantly monitor blood chemistry. The moment they detect the acidic shift, they command the autonomic nervous system to intervene. You likely won't consciously notice the response. Your breathing depth increases, your heart rate elevates, and your cerebral blood vessels dilate. These automatic microadjustments successfully defend your blood's pH. However, they quietly divert finite physiological resources away from high-level cognitive function. To understand how this physical stress alters thought, we have to look up into the neural architecture itself. The brain does not shut down evenly. The neurocognitive cost of this physiological compensation is highly asymmetrical across different neural networks. First, consider algorithmic tasks. These are the brain's basic processing functions, handling simple accuracy, proofreading, and basic arithmetic. Under low-level hypercapnia, these algorithmic pathways remain remarkably resilient and functional. The biological stress is present, but the routine data processing continues uninterrupted. The vulnerability lies elsewhere. It is concentrated in the brain's highly sensitive executive network, located in the prefrontal cortex. This is where the brain handles high-level strategy, crisis response, spatial planning, and complex decision-making. As the physiological cost of mental effort rises due to the retained CO2, these complex executive nodes struggle to synchronize and maintain the arousal needed to sustain performance. Elevated indoor carbon dioxide does not make humans generally incompetent. It specifically degrades our capacity to handle high-stakes strategic problems. We can measure this specific cognitive asymmetry using quantitative data from highly controlled environmental chamber studies conducted at the Lawrence Berkeley National Laboratory and Harvard. To isolate the variables, researchers injected ultra-pure CO2 into perfectly ventilated rooms, pushing the ambient concentration to targets between 1,000 and 2,500 parts per million. Under these pure CO2 conditions, basic algorithmic performance and typing speed did not collapse, exactly as the biological model predicted. To test the vulnerable executive network, they used the Strategic Management Simulation Battery, a tool designed to evaluate high-level decision-making during a crisis. This chart tracks the results across 9 cognitive domains. As the baseline moves from 600 parts per million to 2,500, scores for basic strategy plummet 94%. Yet there is a seemingly paradoxical anomaly in the data. Performance in the focused activity domain actually increased. This is a neurological hyper-focus stress response. The brain fixates on immediate, simple tasks because it lacks the metabolic resources required for broad strategic awareness. At concentrations found in typical meeting rooms, pure carbon dioxide acts directly as an invisible friction on executive leadership and crisis management. But a laboratory chamber is a highly controlled environment. The messy reality of occupied commercial buildings presents a far more complex challenge. Outside of a lab, indoor carbon dioxide almost never rises in isolation. An elevated CO2 reading is mathematically tied to a falling rate of outdoor air ventilation per occupant. When ventilation drops, humans also emit a vast invisible cocktail of odors, exhaled gases, and volatile organic compounds known collectively as bioeffluents. Indoors, CO2 operates as an accurate tracer gas. The gray volumetric field representing CO2 rises in perfect tandem with the green field representing this biological cocktail. This bioeffluent cocktail, not the CO2 itself, triggers acute physical stress, headaches, and a drop in algorithmic work speeds. The true mechanism of harm in a standard building is layered. It is a simultaneous combination of pure carbon dioxide destroying executive function and proxy bioeffluents destroying algorithmic speed and physical comfort. We can assemble this framework, the 5-layer model. Layer 1 is direct physiological shifts, specifically mild hypercapnia. Layer 2 is increased cognitive workload and executive network degradation. Layer 3 is sleep disruption, as autonomic strain spikes cortisol. Layer 4 represents copollutants, the bioeffluent cocktail tracking CO2. Layer 5 is shared air, where CO2 marks the accumulation of infectious aerosols. The exact biological mechanism of harm fluctuates depending on the room and the task, but the engineering solution remains identical across all 5 layers. Controlling indoor carbon dioxide functions as the master lever for mitigating all 5 layers of human degradation in the built environment. Over a single day, humans move through distinct architectural spaces, from a dark bedroom to a dense classroom to a high-stakes corporate meeting room. If an environmental monitor reads 1,200 parts per million of carbon dioxide in any of these rooms, it registers well below the 5,000 ppm occupational hazard limit set by industrial safety agencies to prevent acute asphyxiation. Yet that exact same 1,200 ppm concentration triggers strict intervention protocols if it occurs in a sleeping environment or a primary school, while it is routinely ignored during a transient vehicle commute. Indoor carbon dioxide does not operate as a binary toxin with a single universal medical cliff edge. The biological stakes of a specific parts per million reading fluctuate wildly based on the environment it occupies. To understand true exposure risk, building scientists must decouple the raw CO2 number from universal safety scales and map it directly to the specific cognitive and physiological demands of the human operating cycle. CO2 exposure severity is dictated by specific data streams. Total duration is the primary multiplier. A 2-hour exposure carries different biological weight than an 8-hour cycle. Furthermore, the room's metabolic and cognitive demands alter the threshold for impairment. Sleep differs entirely from strategic decision-making. Raw telemetry is functionally useless for diagnosing building health, until it is intersected with the baseline vulnerabilities of the specific occupants. The bedroom represents the architectural zone with the highest continuous exposure duration in the human lifespan. As occupants breathe behind closed doors and sealed windows, exhaled carbon dioxide steadily accumulates throughout the night, narrowing the partial pressure gradient between the ambient air and the bloodstream. To observe how this building metric intersects with neurological repair, we look at polysomnography. This dual-axis graph maps a steady rise in room CO2 on the top against a hypnogram charting human sleep stages on the bottom. Empirical data demonstrates that as the ambient concentration crosses the 1,000 ppm threshold, overall sleep efficiency measurably degrades. Specifically, as the room concentration crosses 1,300 ppm, the deep sleep valleys on the hypnogram compress significantly. This compression is accompanied by jagged, frequent waking spikes that correlate precisely with the highest carbon dioxide concentrations of the night. The next-day physiological consequences of this disruption are distinct, including a measurable increase in morning salivary cortisol, a primary biomarker for physiological stress. For proper sleep architecture, the operational target must remain below 800 ppm. Sustained overnight averages at or above 1,000 ppm actively degrade physiological restoration and next-day cognition. Moving to the classroom setting, the dynamics shift. High occupant density combined with limited square footage causes a rapid, aggressive rise in ambient carbon dioxide. The vulnerability of this setting is distinct, children engaging in active, high-stakes cognitive development. While 1,000 ppm of pure CO2 is not acutely poisoning children, it acts as a highly accurate proxy for the parallel accumulation of human bioeffluents and stale air that degrade algorithmic task performance. Predictive modeling quantifies this degradation. This bar chart demonstrates expected academic gains when a heavily occupied classroom improves ventilation. Dropping CO2 from 2,100 down to 900 ppm yields an estimated 12% increase in test speed and a 2% reduction in errors. Zooming out, we can chart school attendance. This scatter plot measures the differential between indoor and outdoor CO2 against annual daily presence. Higher indoor-outdoor CO2 differences directly correlate with a 10 to 20% relative increase in student absence rates. Any sustained levels over 1,500 ppm constitute an unacceptable learning environment. Protecting cognitive development demands a strict routine goal of 800 to 1,000 ppm. In the corporate meeting room, the environment demands complex executive function, strategic recalibration, and crisis management. In these high-density offices, carbon dioxide serves a dual metrological purpose. It tracks cognitive decline, and it serves as a proxy for respiratory pathogen risk. The physiological logic of shared air is straightforward. Carbon dioxide is co-exhaled with respiratory aerosols. Tracking the accumulation of the red CO2 gas serves as a highly scalable proxy for estimating the concentration of the blue infectious aerosols in the room. In an untreated, naturally ventilated space, this rebreathed air fraction maps directly to airborne transmission risk. But there is a strict metrological limitation. CO2 cannot identify if a source is actively infectious, it cannot calculate their viral emission rate, and it is blind to close-range exposure dynamics. While CO2 is an excellent baseline proxy for shared air, relying on it as an absolute infection risk meter creates a dangerous vulnerability the moment engineering controls are introduced. That decoupling occurs through specific mechanical interventions, like high-efficiency particulate air filtration and ultraviolet germicidal irradiation. The core function of mechanical air cleaning is actively removing solid and liquid aerosolized particles from the environment. When a HEPA filter activates, the metrics diverge. Blue aerosol particles are vacuumed out, dropping to near zero, while the red CO2 gas persists unaffected at 1,500 ppm. Gas phase carbon dioxide molecules pass directly through particulate filter media unimpeded. The resulting paradox is clear. A room with high CO2 and HEPA filtration has a vastly lower infection risk profile than a room with high CO2 and no filtration. Evaluating building safety requires interpreting gas metrics alongside filtration data. Treating CO2 as the sole indicator of airborne pathogen risk results in a massive analytical blind spot. Pulling back from individual rooms, we see that macro-level building physics operate across different socioeconomic realities. Vulnerability to elevated CO2 scales heavily with spatial footprints and economic constraints. Modern energy efficiency retrofits in low-income housing often aggressively seal building envelopes to save on heating and cooling costs. When these tight envelopes lack dedicated mechanical fresh air systems, they inadvertently trap occupant-generated CO2, moisture, and bioeffluents inside. This creates a compounding dilemma. Natural ventilation, simply opening a window, is often impossible in these environments due to the proximity of outdoor urban pollution, like highway exhaust and black carbon. Poor indoor air quality acts as a critical proxy for health inequalities, compounding existing socioeconomic disparities through the sheer physics of the built environment. The optimal indoor carbon dioxide target is inherently contextual. It is not a single universal number. The biological impact of the exact same metric fluctuates drastically based on the specific cognitive and physiological demands of the occupant at that moment. Across the entire spectrum of scientific literature, sustained high CO2 readings transition into actionable hazards precisely when the human stakes are at their highest. Whether we are sleeping, learning, or executing complex tasks, environmental metrology is only as useful as our ability to map it directly against the vulnerabilities of the human mind and body. When this little, unassuming screen finally turns on, it makes the completely invisible air you breathe suddenly visible. A reading of 1,500 parts per million signals a threshold of cognitive decline. Clinical research shows that when carbon dioxide accumulates from human breath, it impairs decision-making, lowers sleep efficiency, and confirms you are sitting in a pocket of stale, rebreathed air. Today, we are going to build a practical system to fix that. We will identify the exact hardware you need to measure the air, how to read the long-term data, and the proven methods to clear a room. Because possessing raw data is useless without a reliable framework for interpreting and acting upon it. Step 1 is verifying your hardware. You need a device that uses either NDIR or PAS technology to measure absolute carbon dioxide. NDIR stands for non-dispersive infrared. Inside the chamber, an infrared lamp radiates a beam of light. Carbon dioxide molecules specifically absorb that infrared energy at a highly precise wavelength. By measuring the light energy remaining at the end of the path, the sensor calculates the exact CO2 concentration. Compare that to a metal oxide semiconductor, or MOX sensor. These devices do not measure carbon dioxide directly. They measure general volatile organic compounds, and then use an algorithm to estimate an equivalent CO2 value. If you use hand sanitizer nearby, the alcohol vapor triggers a massive, fake spike on the screen. Unboxing new furniture, using cleaning sprays, or even wearing perfume can cause an eCO2 device to report dangerous levels of carbon dioxide, even if the room is empty of people. Relying on these sensors leads to false alarms and wasted HVAC energy. For authentic environmental management, NDIR or PAS is the only acceptable hardware. Once you have an accurate monitor, physical placement dictates the quality of your data. The device must sit in the occupied breathing zone, standard desk height. Keep it out of direct sunlight, away from supply vents blowing fresh air onto the sensors, and out of your direct exhaled breath path. Looking at this chart reveals why checking the screen once a day is insufficient. You must log time series data to understand a room's actual ventilation profile over 24 hours. We start at a flat baseline, the background level of clean outdoor air. As people enter the room, the line curves upward from their exhalations. It hits an occupancy plateau where human output balances against fresh air entering. Finally, when occupants leave, the levels decay back down toward firmly the baseline. Reacting to an isolated spike is a mistake. Long-term trends are the only true indicator of whether your ventilation is adequate. To manage that plateau, you need concrete numerical thresholds to dictate when intervention is necessary. This dashboard breaks down the exact limits. Your optimal target for shared rooms, bedrooms, and offices is right here in the green, between 600 and 800 parts per million. This represents high-performance conditions close to fresh outdoor air. When levels drift above 1,000 parts per million, you enter the orange ACT zone, where clinical studies report cognitive decrements. If the plateau stays above 1,500, you are in the red fix zone, requiring immediate mechanical improvements. It is critical to distinguish these health targets from the much higher OSHA and NIOSH limits. Occupational limits of 5,000 parts per million are designed to prevent acute toxicity in extreme industrial environments, like deep vein mining. Waiting for carbon dioxide to approach these industrial hazard limits in a home or office means you have already accepted severe cognitive degradation. When your data signals a problem, physical air exchange is the only durable method for lowering occupant-generated CO2. You must dilute the indoor air. You achieve this by opening windows and doors when outdoor air is safe, running exhaust fans, or utilizing mechanical units like heat recovery or energy recovery ventilators. Many assume buying high-end HEPA air purifiers will reduce carbon dioxide levels. They do not. HEPA filters are designed to capture solid particulate matter and viruses. Tiny gaseous molecules of carbon dioxide pass through the filter fibers entirely untouched. Purifiers are essential for controlling viruses and smoke, but they must be paired with physical fresh air ventilation to solve the total indoor environment equation. Another pervasive myth is that standard houseplants act as effective air scrubbers for modern rooms. Building air leaks dilute gaseous pollutants exponentially faster than plant leaves can absorb them. To meaningfully impact the CO2 produced by a single family, you would need hundreds of plants packed floor to ceiling in every room. Chemical scrubbers using soda lime are also impractical for residential use. They are economically prohibitive and strictly meant for completely sealed environments. They are used where natural ventilation is physically impossible, such as inside an isolated military submarine engine room. Finally, avoid ozone generators. They have no efficacy in reducing CO2 and are highly reactive, toxic pollutants that induce severe respiratory inflammation. Attempting to bypass basic physical ventilation with biological or chemical shortcuts in normal buildings is an expensive and dangerous failure. To take control of your air, follow 3 non-negotiable rules. Verify you have NDIR hardware, target the 600-800 ppm optimal zone, and prioritize physical dilution. Accurate data gives you the power to manage your shared air environment and protect your cognitive performance. When you verify your environment, you can work and sleep with the confidence that you are operating in a clean, well-ventilated space. Measuring and managing carbon dioxide transforms invisible air quality from a hidden liability into a controllable asset for human performance.